Well, good morning. This is me going to take you through gravitational field and force because we're going to have a fire drill, I believe. So, you should know from higher that you've got Newton's law of gravitation. You've got this mutually attractive force between two large masses, and you've got that value for big G, the gravitational constant, Newton's gravitational constant, 6.67 times 10 to the minus 11. I've just put in the extra few significant figures here just for completeness there. That was originally done by physicist Cavendish, where he basically had large metal spheres and other masses that they would attract and cause a twist in this torsion beam. You can see the torsion beam there, and that degree of twist would then have a light which is reflected off a mirror, and that's how they could detect how much the masses actually attracted each other. So you can look up about Cavendish's experiment if you want to know how that gravitational constant was actually come up with. It's important to draw the distinction between gravitational field as opposed to gravitational force. Force is what we experience as weight. The field is this invisible set of lines, just like you would have a magnetic field or electric field, invisible field lines, which indicate where, if you put a test mass in any particular place, where that mass would go, which direction it would go if it was placed in that point. So if I put a mass here, it'll go in that direction. It'll follow the direction of the field lines. They start in deep space. They always connect in to whatever the mass is, to the planet, so they actually have an ending on the actual planet, and it's that direction. As the field lines get closer together, then there's a greater field. So the greater the density, the greater the field that you're expecting. Gravitational field itself is defined as being the mass per unit, the force per unit mass at that point. So if you've got a mass m where there's a gravitational field g, then the force is equal to the product of the mass and the field. In other words, weight equals mass times gravity, which you've known since first or second year. And the gravitational field is defined as being that force divided by the mass, or force per unit mass. So field exists at any point. The force only exists where you've got a mass in the field of another object. So the definition we've got is then if you've got two masses there, they will experience that force. So this is where Newton's law of gravitation comes from, that you've got the forces are equal to g times one mass times the other mass divided by r squared, that it's an inverse square relationship. If you take that equation then, you say, well, that's the weight, mg, where m2 is the test mass, the small thing that's out away from the Earth, and m1 is the planet, then the weight of the mass times the gravitational field strength is equal to that force of attraction divided by r squared. And r, remember, is from the center of the planet that you're measuring. So you cancel m2 both sides, and you've got gravitational field is g, mass of the planet, divided by this distance from the planet. And that gives you the gravitational field at a point, that radius away from the planet. So that's the equation that you would use for gravitational field. So if we plot that, you'll get an inverse square graph, but one of those two lines is actually not correct, even though I got it off an internet from the website, which is shown below. If we've got g equals gm over r squared, it will go down, it will decline, it will go away as the distance increases, but it's actually the blue line which is correct, because that's measured from the center of the planet. The red line here you wouldn't have, because that's measured from the surface. So you've always got to include the radius of the planet when you're using that equation there for gravitational field. But what you can see is that as you go further away from the planet, the gravitational field decreases until out at infinity, you've got virtually no gravitational field due to the planet. If you've got two objects like the moon and the Earth, midway between the Earth and the moon, you're going to have a gravitational field due to the Earth and a gravitational field due to the moon there. You can actually calculate those two by using g equals gm over r for both of those, and then work out what the resultant field would be by putting yourself in the middle there. So you'll be able to do that in just a moment. So the key things we've just gone through is the definition of gravitational field strength and as being the force per unit mass. You should be able to sketch those field lines and field line patterns around the two planets or a planet-moon system, and then carry out calculations using those relationships for gravitational force and field and the connection between field and force. Okay.